Okay, so in this problem, I'm going to show you something new and advanced, it's also very important in applications, in particular in engineering. So let's consider taking the Laplace transform of a piecewise function like this, right? So we don't see a lot of these piecewise functions in mathematics up until this point because as mathematicians we avoid these kind of thorny objects, but they do exist all the time in reality. So, at a certain point we have to bring these in. So the idea here is that we're going to piece together build a Frankenstein function, right? So it's 0 up into for t less than 4. So this is t, this is my f of t. And then it's a linear function, 3t minus 4 in this range. And then it sort of saturates to the value of 9 after that, right? So I don't know, you could think of this as like a power that's being flipped on in a circuit, right? So it's 0 until we flip it on, and then it's going to have some kind of linear increase, and then it's going to flatline to whatever the generator's output is supposed to be. So this kind of discontinuous, not discontinuous, but piecewise change like this happens all the time in real world scenarios. Okay, so here is a framework for dealing with these kind of functions. And it might seem like it's overcomplicating, but you'll see why we're going to build it in this way when we get to the transform part, right? So just remind you, we're going to try to take the Laplace transform of this function. Okay, so I want to introduce what's called the Heaviside step function, or I just call it the Heaviside function. So the idea, this is a sort of very simple function. It just goes to 1 for t greater than 0, and it's 0 for t less than 0. And the reason for introducing this is the simplest way to build piecewise functions, is by chaining together these Heaviside functions. Okay, so let me just point out here that I can make a more complicated version using a Heaviside function so t minus c, that's just going to shift the origin over to c, right? So that would mean that now my step occurs at c instead of at 0. And then the height will become some g of t. I'm just writing a general function of time there. Because it's 0 before here, it gets zeroed out, right? So whatever this is over here before c doesn't matter at all. And then at c, it'll jump up to this height that we control with the g of t. So you can see how we're building up more complicated functions using this simple sort of Lego Heaviside function there. Okay, so let's think about what happens if we take the Laplace transform of a Heaviside function, right? That's our just unit step at 0. All right, well, we fill it in. And it turns out to be very easy because, well, h of t takes two values. It's either 0 if it's less than for negative numbers, and it's 1 else. So we're only integrating over the points where it's positive and equal to 1. So we just fill in 1 there, and we get that it's 1 over s. Okay, now let's think about taking the Laplace transform of our more general g of t, h of t minus c. And we're going to write this as g of t minus c and h of t minus c. It doesn't matter too much, but it makes our formulas much nicer if we work it out in this way. All right, so fill this in, right? So all I'm doing is applying the definition of the Laplace transform here. And then this is a change of variable, right? So we have a t minus c here, we have a t minus c here. And we want to change variables and make that into something we'll call tau, right? So tau is t minus c, therefore t is tau plus c, right? Just solving d tau dt, right? So this is like u substitution that we do all the time in calculus 1 is equal to 1. So we don't have to change the volume element here, right? So if I change variables from t to tau, then I get h of tau, g of tau. That was by design, right? We wanted to simplify those. d tau, and then up here, I need to plug in for my t, tau plus c. All right, and then I need to change the bounds. So these are in terms of t. So in terms of tau, I subtract c from that. So 0 minus c gives me negative c. Infinity minus c is still infinity. So that bound doesn't need to be updated. Okay, so then, well, h of tau, well, that's just our dummy variable. And so that's 0, and then it's 1 for values greater than 0. And in particular, this negative c here ends up not mattering because if I'm integrating over inputs that are negative, they're going to get zeroed out by the heavy side anyway, right? So anything any input that we put into this integrand that was less than 0 gets zeroed out by the heavy side. So this actually is just e. So you can see I went ahead and distributed here e to the minus sc. That's constant as far as this integral goes. E to the minus s tau, g of tau d tau. Well, that is much simpler, right? So this is some function that depends on s but doesn't depend on the integral times, and this is just the Laplace transform of g. So we get e to the minus sc g of s. So we can easily compute this Laplace transform using this formula here. All right, so let's apply this to our Frankenstein function for this problem. So the first thing that we'll have to do is write this step side or this piecewise function using our heavy sides. All right, so we have two changes here, right? This and this, right? So there's a change at t equals 4 and a change at t equals 7. So what happens at t equals 4? Well, before that it's 0, so we don't need to worry about that, right? So heavy side will zero everything out for anything to the left of it. And then the height's going to change to being determined by this function, so times 3t minus 4. Great, so that takes care of that change. And it'll keep going, right? So like if we just left it as that, we would have just our straight line going up there. So what happens at this next thing is that we need to stop using the linear function and we need to just stick at 9, right? So you can see I did plus 9 h t minus 7. So this means the value of 9 turns on for t greater than 7. But the problem here is that like I would have this and that, right? Because this will be on and this will be on. So this is what I call the off switch, right? So we're going to turn this function, 3 of t minus 4, we're going to turn it off by just subtracting it off. So this will come on for t greater than 7 and cancel that value out, leaving us with, so if I put in like t equals 8, I would get this minus this, those would cancel, plus 9, and I would get my 9 value there. So that's very common, is you're going to want to turn on, and then when it changes again to a different function, you just turn it off by subtracting it off at the off point. All right, so one last little thing here to do would be to use my formula here. I want to write this as g of t minus c, h of t minus c. Sorry. So we can always do that with a linear function like this. So I'm just going to distribute and combine it, right? Both of these are times t minus 7. So let's distribute that, and I get minus 3t plus 12 plus 9. And I want a t minus 7 here. Well, it turns out if I just factor out a negative 3, I get t minus 7, t minus 7, t minus 4, t minus 4, and we're all paired up and ready to apply our formula. So the first one, when I transform it, right, you get e to the minus cs g of s, s greater than 0, right? So you get, that's my c value, so e to the minus cs, and then the Laplace transform of 3 times t minus 4. Still have to work that out. E to the minus 7s, right, that comes from my heavy side. And then the Laplace transform of negative 3t minus 7. And then, so these are linear functions. So I can pull the 3 out. And then the Laplace transform of t is 1 over s squared. The Laplace transform of negative 1 is just 1 over s. So this is 1 over s squared. Same thing here, minus 3 comes out. Laplace transform of t is 1 over s squared. Laplace transform of -7 is -7 over s. And lo and behold, we've computed the Laplace transform of our on switch, our real life on switch.